Pressure is building beneath one of the most geologically active regions on Earth, yet the movement is so slow it escapes daily notice. Coastlines appear unchanged from one year to the next, harbors still cradle boats as they always have, and cities continue to expand toward the sea. But precise measurements tell a different story, one that raises difficult questions. How can an entire nation stand firm while parts of it are quietly lowering into the ocean? Why do some coastal zones drop while others rise? And what does it mean for a country positioned directly on a shifting boundary between massive tectonic forces? Across New Zealand, a subtle but persistent transformation is underway. The land is not uniformly stable. Instead, it behaves like a vast, uneven platform responding to stresses deep within the earth. In certain coastal areas, the ground is gradually subsiding, lowering by mere millimeters each year, yet accumulating into measurable change over decades. This is not a sudden collapse, nor a dramatic event visible to the naked eye. It is a slow adjustment, driven by forces operating far below the surface. The explanation begins with geography, but not the kind visible on maps alone. New Zealand straddles the boundary between the Pacific Plate and the Australian Plate, two enormous slabs of the Earth's crust that are constantly moving. Their interaction defines the region's seismic and volcanic character. In some places, one plate slides past the other. In others, one is forced beneath the other in a process known as subduction. This continuous motion does not simply produce earthquakes, it also reshapes the land in slower, less perceptible ways. Measurements collected over time reveal that about 40% of New Zealand's coastline is experiencing gradual subsidence. The rate is typically between 1 and 5 millimeters per year, equivalent to roughly 0.04 to 0.2 inches annually. At first glance, such figures seem insignificant. Yet over a span of 50 years, even a modest rate of 2 millimeters per year results in a drop of about 100 millimeters, or nearly 4 inches. Over a century, that change doubles. In regions already close to sea level, this shift can alter drainage patterns, increase flood risk, and subtly redraw the boundary between land and sea. Urban areas are not exempt. In Auckland, sections of reclaimed land along the waterfront show measurable downward movement. The city has expanded significantly over former tidal flats, areas that were never naturally elevated above sea level. These reclaimed zones are particularly sensitive, as the underlying sediments compress over time under the weight of development. Combined with tectonic influences, this creates a compound effect where natural and human factors overlap. Further south, Wellington sits near one of the most complex tectonic junctions in the country. Here, the boundary between plates transitions from a subduction zone to a strike-slip fault system. This complexity leads to uneven vertical motion. Some sections of land rise while others sink. Instruments detect these movements with increasing precision, revealing patterns that were once impossible to observe. The city's coastal edges, in particular, display signs of gradual subsidence that align with deeper structural adjustments underground. In Christchurch, the situation carries additional layers. Built on alluvial sediments and shaped by past seismic activity, parts of the city experienced noticeable land-level changes following major earthquakes. While those events cause sudden shifts, the longer-term trend includes ongoing subsidence in certain low-lying districts. This is not uniform across the region. Instead, it reflects variations in soil composition, groundwater conditions, and tectonic stress distribution. The mechanics behind this phenomenon are tied to how stress accumulates and is released along plate boundaries. As the Pacific Plate pushes against or beneath the Australian Plate, energy builds up over time. Some of this energy is released abruptly through earthquakes, but not all of it. A portion is dissipated gradually, causing the crust to bend, flex, and adjust. This deformation can result in uplift in one area and subsidence in another, often within relatively short distances. Satellite-based measurements have become essential in tracking these changes. By using systems capable of detecting ground movement down to a few millimeters, scientists can map vertical land motion across wide regions. These observations confirm that subsidence is not random. It follows patterns linked to tectonic structures, sediment layers, and historical stress accumulation. In some coastal stretches, the downward movement is steady and continuous. In others, it occurs in small increments, reflecting episodic adjustments deep underground. One of the more subtle contributors to subsidence lies beneath the surface in the form of sediment compaction. Coastal plains and reclaimed areas are often composed of loosely packed materials such as sand, silt, and clay. Over time, these materials settle under their own weight and the additional load of buildings and infrastructure. This process alone can lead to gradual sinking, even in the absence of tectonic activity. When combined with plate boundary dynamics, the effect becomes more pronounced. Sea level adds another dimension to the issue. While the land is moving downward in certain areas, global sea levels are rising due to thermal expansion and melting ice. The interaction between these two processes creates what is known as relative sea level rise. Even if the ocean were stable, subsiding land would experience increasing encroachment by water. Conversely, even stable land would face challenges from rising seas. When both occur together, the impact intensifies. Despite these changes, the pace remains slow enough that it rarely attracts immediate attention. A drop of a few millimeters per year does not crack roads overnight or flood entire neighborhoods in a single season. Instead, the effects accumulate quietly. Drainage systems become less efficient. High tides reach slightly further inland. Storm surges penetrate areas that once remained dry. Over decades, these incremental shifts begin to reshape coastal landscapes. Historical records provide context for understanding the scale of change. In some regions, comparisons between old survey data and modern measurements reveal cumulative subsidence of several centimeters over the past century. This aligns with the expected rates derived from current observations. It also underscores the importance of long-term monitoring, as short-term fluctuations can obscure underlying trends. The distribution of subsidence is uneven, reflecting the complexity of New Zealand's geological framework. Along the eastern coast of the North Island, where subduction is more active, certain areas show consistent downward movement. In contrast, parts of the western coast experience relative stability or even uplift. This contrast highlights the dynamic balance of forces at play, with different segments of the crust responding in distinct ways to the same overarching tectonic interaction. Inland areas are not entirely immune, though the effects are generally less pronounced. The influence of plate boundary processes extends beyond the immediate coastline, affecting broader regions through subtle deformation. However, the most visible consequences tend to occur where land meets sea, as even small vertical changes can alter tidal dynamics and coastal processes. Technological advances have made it possible to detect and analyze these movements with unprecedented clarity. Continuous monitoring stations, satellite data, and geodetic surveys combine to create detailed maps of land motion. These tools reveal not only where subsidence is occurring, but also how it evolves over time. Patterns emerge that correlate with known fault lines, sediment basins, and zones of tectonic compression or extension. At first glance, the idea of a country slowly sinking may suggest a uniform descent, but the reality is far more complex. New Zealand is not uniformly lowering into the ocean. Instead, it is shifting, tilting, and adjusting in response to deep geological forces. Some areas rise, while others fall, creating a constantly changing topography that reflects the ongoing interaction of tectonic plates. This complexity is what makes the situation both challenging and revealing. The same forces that cause subsidence in one location can produce uplift in another, sometimes only a few kilometers away. This means that understanding the phenomenon requires a detailed, localized approach rather than broad generalizations. Each coastal segment has its own characteristics, influenced by a combination of tectonic setting, sediment composition, and historical stress patterns. The gradual nature of subsidence also raises questions about perception and awareness. Changes that occur over decades often go unnoticed by individuals, even as they accumulate into significant shifts. It is only through systematic measurement and long-term observation that the full extent becomes clear. Without these tools, the process would remain largely invisible, masked by the slow pace at which it unfolds. Beneath the surface, the interaction between the Pacific and Australian plates continues without pause. The boundary does not rest, and the forces it generates do not diminish. Instead, they shape the landscape in ways both sudden and gradual, from earthquakes that alter the ground in seconds to subsidence that unfolds over generations. The visible environment reflects only a fraction of this activity, with much of the motion occurring deep underground. As the data accumulates, a clearer picture begins to form, though it is not a simple one. The patterns of subsidence align with known geological structures, yet they also reveal new complexities. Areas once thought stable show signs of movement, while others behave differently than expected. These findings challenge assumptions and highlight the need for continuous observation. The quiet lowering of certain coastal areas is not an isolated phenomenon. It is part of a broader system of tectonic adjustment that defines New Zealand's landscape. Each millimetre of change represents a response to forces that operate on a scale far beyond human experience. Understanding these changes requires looking beyond immediate observations and considering the deeper processes that drive them. The question remains how these gradual shifts will evolve over time, and what underlying mechanisms determine where subsidence occurs versus uplift. Patterns are emerging, but they are not yet fully understood. The interaction between tectonic stress, sediment behavior, and external factors such as sea level continues to produce outcomes that are both predictable in trend and complex in detail. The deeper explanation, however, lies in a less obvious process that does not always produce earthquakes or dramatic surface features, yet plays a crucial role in shaping vertical land movement. It operates silently along parts of the plate boundary, redistributing stress in a way that influences whether the land rises or sinks. This mechanism, often overlooked in broader discussions of tectonics, begins to explain why such a large portion of the coastline is gradually subsiding, while other sections remain stable or even elevate. It is within this subtle process that the full picture starts to emerge, pointing toward a hidden driver that will become clearer as the evidence unfolds further. The deeper mechanism shaping this uneven vertical motion becomes clearer when examining how stress is transferred along the boundary between the Pacific Plate and the Australian Plate. Not all movement along this boundary occurs in sudden ruptures. A significant portion unfolds through what is known as slow slip, a process in which sections of the plate interface move gradually over weeks, months, or even years without producing strong earthquakes. This motion does not release all accumulated stress. Instead, it redistributes it, altering the balance of forces across adjacent regions of the crust. Along the eastern margin of the North Island, the Pacific Plate is being forced beneath the Australian Plate in a subduction system that extends for hundreds of kilometres. This process bends the overriding plate downward near the coast while uplifting regions further inland. The bending is not uniform. It creates a broad, gentle warping of the land, similar to a flexible surface being pressed from below. Coastal sections that lie above the descending slab tend to experience subsidence, while areas further inland may rise slightly as the crust adjusts. This bending is compounded by the physical properties of the crust itself. The outer layers of the Earth in this region are not rigid blocks, but complex assemblies of rock types with varying strengths and densities. Sedimentary basins, which are common along much of the coastline, respond differently to stress compared to older, more consolidated rock formations. These basins can compress under pressure, amplifying the downward motion already induced by tectonic forces. In Wellington, this interaction is particularly intricate. The region sits near the transition between subduction to the north and a major strike-slip fault system to the south. This transition zone creates a patchwork of stress regimes. Some faults accommodate horizontal movement, while others allow vertical adjustments. The combined effect produces localized zones of subsidence interspersed with areas of uplift. Measurements show that even within short distances, the direction and magnitude of vertical motion can vary significantly. Further north, in regions influenced more directly by subduction, the pattern becomes clearer. The overriding plate bends downward as it is dragged toward the subduction interface. This downward flexure contributes to the gradual sinking observed along parts of the coastline. However, this is not a continuous, smooth process. It occurs in cycles, influenced by the timing and location of slow slip events. During these episodes, portions of the plate boundary shift slightly, relieving some stress while transferring it elsewhere. The result is a dynamic system in which subsidence rates can fluctuate over time. The role of fluids within the crust adds another layer of complexity. At depths of several kilometers, water trapped within sediments and rocks can become pressurized as it is subjected to increasing temperature and pressure conditions. These fluids reduce friction along fault surfaces, making it easier for slow slip to occur. At the same time, they influence how stress is distributed, affecting whether a particular area experiences uplift or subsidence. This interplay between rock mechanics and fluid pressure is a key factor in understanding why subsidence is concentrated in certain zones. In Auckland, tectonic influences are less direct but still present. The city lies further from the main subduction interface, yet it is not isolated from regional stress patterns. The crust here responds more subtly, with smaller rates of vertical movement. However, the presence of volcanic fields and underlying sedimentary layers introduces additional variables. Compaction of these layers, combined with minor tectonic adjustments, contributes to measurable subsidence in specific coastal and reclaimed areas. The situation in Christchurch highlights how past geological events continue to shape present-day conditions. The region sits atop thick deposits of alluvial sediments laid down over thousands of years by rivers and coastal processes. These sediments are highly compressible. When subjected to stress, whether from tectonic forces or the weight of urban development, they gradually compact. This compaction leads to subsidence that can persist long after the initial stress is applied. The South Island presents a different tectonic environment dominated by the Alpine Fault, a major boundary where the two plates slide past each other. While this motion is primarily horizontal, it is not purely so. The interaction also produces vertical components, leading to uplift in some regions and subsidence in others. The Southern Alps themselves are the result of this uplift, rising as the crust is compressed and forced upward. Meanwhile, adjacent basins may experience gradual sinking as material is redistributed. The contrast between uplift and subsidence across relatively short distances is a defining feature of New Zealand's geology. It reflects the balance between compressional and extensional forces acting simultaneously along different segments of the plate boundary. Where compression dominates, the land tends to rise. Where extension or bending occurs, it tends to sink. These processes are not static. They evolve as the plates continue to move, altering the distribution of stress over time. Another factor influencing subsidence is isostatic adjustment, a process in which the Earth's crust responds to changes in weight. While often associated with glacial regions, the principle applies more broadly. In areas where sediments accumulate or where erosion removes material, the crust adjusts to maintain equilibrium. In coastal zones, the deposition of sediments can add weight, contributing to gradual sinking. Conversely, erosion inland can lead to slight uplift as mass is redistributed. The interaction between tectonic subsidence and rising sea levels creates a compounded effect along vulnerable coastlines. Even a modest rate of land subsidence, when combined with increasing ocean levels, accelerates the relative encroachment of the sea. This does not necessarily result in immediate flooding, but it alters the frequency and extent of coastal inundation. High tides reach further inland, and storm-driven surges become more impactful. Over time, these changes influence coastal geomorphology, Shorelines may retreat as erosion outpaces sediment deposition. Wetlands can expand or shift location, adapting to new water levels. In some cases, natural barriers such as dunes or spits may struggle to keep pace with the combined effects of subsidence and sea level rise. These transformations occur gradually, often becoming noticeable only when compared across decades. The data supporting these observations comes from a combination of satellite measurements, ground-based instruments, and historical records. Techniques such as interferometric radar allow for the detection of minute changes in land elevation across large areas. These measurements confirm that subsidence is not only widespread, but also consistent with the underlying tectonic framework. Patterns align with known fault systems and subduction zones, reinforcing the link between deep geological processes and surface-level changes. Despite the clarity provided by modern technology, uncertainties remain. The exact distribution of subsidence is influenced by numerous variables, including the geometry of the plate boundary, the properties of the crust, and the behavior of fluids at depth. Small changes in any of these factors can alter local outcomes. This makes precise predictions challenging, particularly over longer time scales. What becomes increasingly evident is that the gradual sinking observed along parts of New Zealand's coastline is not an isolated anomaly, but a natural consequence of its tectonic setting. The country exists in a state of continuous adjustment, shaped by forces that operate over vast spatial and temporal scales. Each millimeter of movement reflects a balance between competing processes, from plate interactions to sediment dynamics. If you found this breakdown clear and informative, make sure to like, share, and subscribe for more in-depth reports like this. And do not forget to tap that hype icon to help this reach a wider audience and keep more people informed about the changes happening beneath our feet.